Alright, let's read the equation first. Rho C alpha by rho T is equal to minus del dot n alpha plus R alpha, where alpha ranges from 1 to number of species in the mixture. C alpha is the molar concentration of species alpha in mole per meter cube or kilomole per meter cube. N alpha is the molar flux of species alpha. R alpha is the rate of molar production or consumption due to chemical reaction.
This equation basically says that the rate of change of concentration of a species depends on how much is coming in or going out through flux and how much is being produced or consumed during the reaction, which is being taking place at that point.
Let's go one term at a time. First, dou C alpha by dou T. This is the local accumulation of the species. It's how the concentration changes over time at a fixed point in space.
Okay, so the next thing is minus del dot n alpha. This term captures spatial changes in molar flux. In simple terms, we could explain how the species moves in or out in a small volume. If more is leaving than entering, the concentration drops.
And the last term, R alpha, adds the chemical reaction element. It can be positive if the species is being formed or negative if it is being consumed.
Now let's talk about n alpha. The molar flux, this is where things get rich. It's composed of two main components. First is the convective flux. This is the transport due to the bulk motion of the fluid. It's like the whole fluid carrying the species along with it. So the formula following it is n alpha of convective flux is equal to C alpha, which is the concentration of that particular alpha particles species and into its corresponding velocity. And next, the diffusive flux. This is transport due to concentration gradient. It is governed by basically the Fick's law. So Fick's law basically tells that n alpha, which is the flux during diffusion, equal to negative of d alpha into delta of concentration difference. So dA here refers to the diffusion coefficient.
So we get the total molar flux equation as n alpha is equal to C alpha times V minus D alpha times del dot Cl. That's a beautiful mix of physics, convection and chemistry, diffusion and reaction.
Okay, so why do we use this equation? The first thing is because it let us track species in dynamic system. Because the system will be moving and like CO2 spreads in a greenhouse gas or how the pollutants disperse in a river, the same way it follows.
This equation is also essential in reactor design. Whether it's a PFR, CSTR, catalytic surface, you need this equation to model how reactants are consumed and products are formed from it.
And if you are working on membrane systems, combustion, pharmacokinetics, or even semiconductors, this equation is a starting point for every process.
Let us zoom out again. In transport phenomena, we deal with three types of transports. That is momentum transport, involving fluid motion, heat transport, which involves temperature gradients, and mass transport, which involves the movement of species and mixture. And each of them has the same structure. Accumulation is equal to N minus out plus generation.
This equation is the mass transport analogy, and understanding it is the key to predicting how fast the drug diffuses into the bloodstream and controlling the combustion in a reaction or in reaction engines. And the next, optimizing chemical yield in a reactor, managing oxygen supply in tissues, engineering.
In short, it's about understanding how matter moves and transforms. And that's what transport phenomena is all about.
Now, let's give a quick example. Imagine a gas absorber tower where CO2 is being absorbed by water. So, the bulk gas flow provides convective transport through water, and CO2 diffuses into the water phase, and inside the water, it may react with a base like NaOH. All the three parts of this equation are active, and if you want to model it accurately, you can't ignore any of them. Now, let's start by reading this equation. Del C alpha by dt, which is equal to del dot C alpha V star minus del dot J alpha star plus R alpha, for R alpha is equal to 1, 2, 3 up to n, where C alpha is the molar concentration of alpha species and V star is the molar average velocity and J alpha is the diffusive molar flux relative to V star, which is average velocity, and R alpha is the rate of generation or consumption due to chemical reaction.
Now we'll break down the terms. First is the accumulation term, which is dou C alpha by dou T. This term tells us how concentration of species alpha changes over time and affects location. It represents the local accumulation.
Exactly. It's crucial in transient processes like startup, shutdown or pulse injection in a reactor. If there is no accumulation term or that is steady state, this term drops out to zero. Next, the convective term, which is del dot C alpha into V star. This is where the bulk transport comes into picture. Here we use V star, which is the molar average velocity, which defined as V star is equals to summation from alpha is equals to 1 to n particles C alpha into V alpha divided by summation alpha, which is equals to 1 to n C alpha, or that is equal to 1 by C, which is the total concentration, into summation of alpha from 1 to n C alpha into V alpha, where C alpha is the concentration of alpha particle and velocity V alpha is the velocity of the particle alpha.
So, unlike the mass average velocity, which is weighted by mass, this is weighted by molar concentration. We use it in ideal gas systems, low density flows, or in systems where molar ratios are more relevant than mass, like in reaction stoichiometry. Now we move to the next term, which is diffusive flux term, that is minus del dot J alpha star. Now this one is a bit subtle. J alpha star is the diffusive molar flux relative to molar average velocity.
Yeah, that's right. It captures how species alpha moves compared to the average bulk molar motion. If there is a concentration gradient, species diffuses from higher concentration to lower concentration, which is the classic fixed law diffusion. So, by the formula J alpha star, which is equals to minus of D alpha into gradient of C alpha. It is true for ideal binary mixture.
So, diffusion and convection are decoupled. This makes analysis and modeling more easier, especially when reactions are involved.
So now coming to the reaction term, which is R alpha. This term represents the chemical sources or sink of species alpha. It's positive when a species is produced and negative when it is consumed.
And it is essential when modeling reactors, biological systems, or combustion. It's where chemistry meets transport.
So now the question poses here, so why do we use this molar formulation instead of mass based on one? So the answer for this would be, in gas phase system it's easier to track moles due to ideal gas law equation. And next, the reactions are typically written in molar units. And the third is, it integrates clearly with stoichiometry and following with thermodynamics.
Exactly, Kaushik. It's also very useful in multi-component diffusion systems and microreactor modeling, where molar effects dominate over time.
So now, coming to the conclusion, if we sum the total species equation across all the species, summing from alpha is equals to 1 to n particles, we get C, the total concentration, is equals to sigma alpha 1 to n C alpha, and resulting equation would be dou C by dou T, which is equal to minus del dot C into velocity star V star plus sigma alpha is equals to 1 to n R alpha.
This is like the continuity equation, but for moles instead of mass. It tells us how the total molar concentration changes.
And it has two big uses. So coming to the first one, ensures the system's overall conservation of mass and moles, and then helps in closing the system when combining with the momentum and energy equations.
So what is its significance in transport phenomena? Let's now place this in the bigger picture of transport phenomena. Remember the classic three: momentum transport, energy transport, and mass transport.
This molar formulation is the mass transport counterpart of these other equations, and together they form a foundation of all continuum transport modeling in chemical engineering, biochemical engineering, and environmental modeling and material science.
In microfluidics, semiconductor manufacturing, electrochemistry, everywhere.
And coming to the real life example, so picture this: an electrolyzer where H2 and O2 are produced by water splitting. You have convection carrying bubble upward and diffusion of H2 from the electrode and reaction at the catalyst surface. This is the classic example in your day-to-day life where you can see all the three processes happening there. This equation model every step of that process.
Molar based equivalent. Del dot B star is equal to 1 by C summation of alpha from 1 to n R alpha. This is a bound shell. It means that if there are chemical reactions, the velocity field diverges or converges based on whether moles are created or destroyed. In the absence of summation R alpha equal to 0, and we are back to the familiar, which is del dot B star is equal to 0.
Okay.
Now we look at the final equation, which is C times dou x alpha by dou t plus B star del xa is equal to minus del dot Ja star plus R alpha minus x alpha into summation of beta from 1 to n R beta. Now we look at the meaning and significance of every term. So C signifies the total molar concentration. X alpha, which is equal to C alpha by C, is the mole fraction of species alpha. V star dot del xa is the convective transport of mole fractions. Del dot J alpha star is the diffusive transport of species alpha. R alpha is the net molar rate of production of species alpha, and X alpha into summation of R beta is the correction term accounting for the effect of reactions on total molar concentration.
The convective transport, which is C times V star into del dot x alpha. This represents the movement of species with the bulk flow of the fluid based on molar average velocity. If the mixture moves, mole fraction change, even if there is no reaction.
Diffusive transport, which is minus del dot J alpha star. This captures how species spread out due to concentration gradients. Remember, diffusion doesn't mean bulk movement. Species just naturally move from high to low concentration.
Next, the reaction term. As we have discussed earlier, R alpha is the reaction term, which is the rate at which the species alpha is being produced or consumed during the reaction. This is where stoichiometric kinetics and reactor design comes into play.
Next, the correction term, which is minus x alpha into summation of R alpha from beta equal to 1 to n. This is the sneaky important term. Even if a species isn't reacting, its mole fraction changes when the total number of moles changes due to other species reactions. For example, if hydrogen and oxygen react to form water, the total number of moles drops and all of the mole fractions shift, even for inert species.
Yeah, exactly. So now why we are dealing with mole fractions? So here is why we are switching to mole fraction. They are normalized. So you can compare across all the systems. And next, they directly plug into equilibrium relations and reaction rates. And third thing is they simplify boundary conditions in multi-phase systems, which is the topic of discussion. And last, most chemical kinetic models use mole fractions or partial pressures rather than mass fraction.
So what is its practical relevance? In combustion, mole fractions matter because it tracks oxygen or fuel ratios over time. In catalysis, it models how reactants or products build up. In bioreactors, we can understand nutrient or byproduct evolution using mole fractions. In air quality monitoring, we can track pollutant fractions in air mixtures. So, why this equation matters in transport phenomena? This equation lets you model species individually, but also how they interact collectively. That's the magic.
Exactly, true. It captures couple transport-less reaction, which is the soul of chemical engineering. If you are modeling real systems, you can't ignore this fact. Now let's start with the continuity equation for mass as shown in figure. Dou rho by dou t, which is equal to minus del dot rho d. This tells us the rate of change of density rho in a fluid volume. It is derived from mass conservation and it reflects net mass inflow and outflow of the system.
And if the fluid is incompressible, meaning density is constant, this simplifies to minus del dot B is equal to 0. This is what we call the incompressibility condition.
Now coming to why mass fraction is used. Mass fraction W alpha represents how much of the component alpha is in a mixture by mass. This brings us to the mass-based species conservation equation, which is rho times dou W alpha by dou T plus V dot del W alpha, which is equal to minus del dot J alpha plus R alpha. Here breaking down the equation in simplified form. So rho is equals to mass density of the mixture, V is equals to mass average velocity, J alpha is the diffusive mass flux or of the species alpha, and R alpha is the rate of reduction of consumption due to chemical reaction.
Mass-based formulations are essential in combustion, polluted dispersion and multi-phase flows, where mass transfer is critical and bulk motion dominates.
Now let us move to the molar form. The equation which is introduced here is dou C alpha by dou T, which is equal to minus del dot N alpha plus R alpha. Here the terms which describe the equation are C alpha is the molar concentration and its units are mole per meter cube, and N alpha is the molar flux and R alpha is the molar production rate.
The next equation splits the flux as dou C alpha by dou T is equal to minus del dot C alpha V star minus del dot J alpha star plus R alpha. Here V star is the molar average velocity, the diffusive part J alpha star shows how a species moves relative to its average motion.
And next, why molar versus mass? Like the question would be, why we are using a mass flux instead molar flux? So the answer would be given by Richie. So yes.
Molar formulations are natural fits for chemical kinetics, electrochemical reactions, catalysis and biochemical systems. Why? Because reactions are governed by molar ratios.
So mass-based forms are used where density variation dominates. So the example where majorly it lies are aerospace, compressible flows and energy systems. And these are the systems and these are the examples where we use mass form.
The final species conservation equation becomes C times dou x alpha by dou t plus V star dot del x alpha is equal to del dot J alpha star plus R alpha minus x alpha times summation beta equal to 1 to n R beta.
Here x alpha is concentration of alpha particle divided by total concentration of the species is the mole fraction, and the last term accounts for how many total moles count changes due to reaction.
This is perfect for multi-component reacting systems, compression, atmospheric chemistry, drug delivery, you name it.
So,
the next equation would be binary systems and Fick's law, which is rho times dou WA by dou T plus V dot del WA is equal to rho DAV del square WA plus RA.
this is the simplified version for binary system using Fick's law. You will see this in gas diffusion experiment and membrane separation.
Using a constant diffusion coefficient simplifies numerical modeling and gives intuitive insights into diffusion behavior.
Now, common misconceptions which will be addressed during the study is you don't always need molar forms for reactant systems, especially if you are tracking bulk mass transfer. And next, mass and molar forms are not interchangeable without careful transformation. This is the key point to be noticed. And next is diffusion is not a loss process. It redistributes material without changing the total amount. This is the term which is used for mass conservation.
Coming to the equation, C times dou xa by dou t plus v star dot del xa is equal to dab del square xa plus xara minus xarb. Now we look at the part term by term breakdown of the equation. Alright Kaushik, let's get into the terms. Start us off.
The left hand side, the time derivative and the convective transport, which is C times dou xa by dou t plus v star times del xa, which is C which is total molar concentration of the mixture. It's the scaling factor.
Now let's look at the equation, which is C times dou xa by dou t plus v star dot del xa is equal to dab times del square xa plus xara minus xarb. Now we look at the term by term breakdown of this equation. Alright Kaushik, let's get into terms. Will you start us off?
Okay, so starting with the left hand side, the time derivative and the convective transport. So the part comes into be C times dou x by dou t plus v star dot del xa. Here C stands for the total concentration of the molar of the mixture. It's the scaling factor here because we are dealing with the mole fraction, and dou xa by dou t, this is the local unsteady state change of mole fraction over a period of time, and v star dot del xa, which is the convective transport, how species A is carried along by the molar average velocity field.
Next is the right hand side, diffusion and reaction. dab times del square xa plus in bracket xara minus xarb. Here the first term, which is dab times del square xa, is the frequent diffusion, which smooths out gradients in mole fractions in molecular diffusion, and the second term xara minus xarb is the reaction correction term. This is very important. It shows how chemical reactions can redistribute mole fractions even if total molar concentration stays constant. Now let's look at the connection of this equation with the previous one.
Okay.
How does this compare with mass-based counterpart? Why even bother with a molar formulation?
Oh, that's a great question. Now coming back to the equation in the previous one in terms of mass fraction, which is WA, and this uses the mass average velocity V in contrast to the equation above, which uses molar fraction. So
the equation 18 is in mole fractions XA and uses molar average velocity V star, and most importantly, it is often preferred when chemical reactions are involved. Why? Because chemical reaction conserve moles more intuitively in many cases. Stoichiometry is easier to track in molar units. When analyzing reacting flows, like in combustion or gas-based catalysis, this form gives cleaner insight into how the species changes with time.
now why molar form? Why not to stick with the mass? So, but hold on. Some might ask, we already have mass conservation. Why do we need molar conservation equation?
The golden question. So the following are the reasons we use molar conservation. First is, chemical reactions are naturally molar. Reaction rates, stoichiometry, equilibrium constants, they are all defined in molar units. And it is easier to balance and interpret. Second is, simplicity in gas phases. In ideal gases, molar concentration is proportional to partial pressure. That makes equations elegant in systems like combustion and vapor diffusion. Third is cleaner treatment of reactions. In the molar form, The divergence of molar velocity includes source terms from reactions, unlike mass form where density changes are more complex. Lastly, thermodynamic consistency. Many thermodynamic models are molar based, so using mole based transport aligns with property prediction and gives energy minimization.